Okay, let's start our lecture number 9, and now we move on to consider problems governed by Laplace's equation in spherical coordinates today. In the next class we are going to talk about the problem of solving Laplace's equation in cylindrical coordinates when the potential depends on 3 coordinates. So today's plan, we are going to follow this summary. We're going to talk about the technique that we started to talk about last class on separation of variables in spherical coordinates. Now the product solution, how it what type of functions result from the process. Also, and as one part of the solution involves the Legendre polynomials and its properties, orthogonality properties, that we are going to talk about. We are also going to describe a powerful technique initially in terms of Legendre polynomials, which is the expansion of the inverse function. The inverse function appears in several formulas in electromagnetic theory, and it's very important to be able to expand this function in normal modes or in normal orthogonal functions. Okay, so we have a way to do that. Then we're going to talk about associated Legendre polynomials, spherical harmonics, and we conclude with the addition theorem and its corresponding proof. I'd like to make an announcement that I started, and I will do that back to the first lecture. In those videos, in the video description, for people who just pick a video in the middle of a playlist, not exactly knowing what's the context of those videos. I mean, this is a course, right? You can find information on the course on the description of the video. But in addition, what is new now is that we are going to put the landmark points on the description, or the points where a given topic is treated, and the time points. So you just click on the time point, you go directly to that point in the video. So it's gonna, I mean, some people have different backgrounds, and they might want to skip some part of the lecture, so they can go straight to the point that they are interested in. So this is very useful for people who want to learn something that is not very clear in their minds, and that is treated in our course. References for this class: Jackson, sections 3.1, 2, 3, 3.5, and 3.6, and African chapter 12 talks about those elements of the lecture. So let's go back to spherical coordinates, and let's look at the Laplacian spherical coordinates. It assumes a more complicated structure now, right? We have this combination of derivatives, second order derivatives, the radial. We have a square inside of the first derivative, and another derivative comes in here. We have this denominator. We have the polar angle derivative. Then we have a sine theta. And this Laplacian comes from our general form treated in in the first part of the course, which was the review on vector algebra and operators. And the derivative in the azimuth angle is this type of term here. You can demonstrate, just let you do that as a exercise, that this derivative here, if you see, you have r squared outside r squared inside, one derivative inside, and one of the whole thing outside. This can be cast in this form here, okay? It's more useful in treating the solution of Laplace's equation. We can put them 1 over r and the second derivative of the product r phi, okay? So let's use the same technique. We are going to assume, for simplicity, okay, that the product r phi, just to gain some time. Otherwise, we would lose some time remaking the whole definition. So we are going to gain some time. Just define instead of phi, but we are going to define r phi as a product of three independent functions. One for the radial coordinate, one for the polar, one for the azimuthal coordinates. So when you do that, for instance, let me transpose this to my calculation here. Because just gonna do one of those. Let's do some of this. Right? We are assuming here that r phi equals to, I'm going to drop the coordinate, explicit coordinate terms, so it's just going to show the function themselves. U times p of theta and q of phi. So, and then we have a derivative, radial derivative is 1 over r. The r2, in fact, is partial, right? Of r phi. When we do that, it's going to be pq goes out of the derivative because it doesn't depend on r, right? So it's going to be pq over r, the second derivative of u. That's this first term here. The second term there, we're going to have d phi d theta equals to uq dp d theta, right? And sine theta d phi d theta, so we have d theta, right? So that's going to be, in fact, I have an r, I forgot this r here, right? So this is going to be uq over r. So this is going to be uq over r, total derivative now because it's a function of a single variable, sine theta dp d theta, right? So you see that the radial term has 1 over r, the theta term has also 1 over r, both have r squared, I'm sorry, yeah, I think it's correct. I'm mixing this. I should just erase this one here. I put the other ones so it's going to be easy to understand. Put this guy there. That's how it is. So erase this. So this one gives this thing here, right? With an r. So the first term just gives pq over r squared. This is second derivative, sorry. Right? Plus second term, in fact, let me just, because has been some time since I did this calculation, so I'm taking some time to do it, but just notice here. These are here, okay, so it's going to be easier. It's going to be like this. These are here, enters here. So that makes it easier. R phi, right? And also here, right? This one here. So we have also R phi. So if R phi is UPQ, so we don't have this. So now let me do it again, okay? Where is it? Here. So this first term here, let me just fix here. When I do that, that's the first term. The second term is derivative of, sorry about that, folks. I'm kind of rusty on this one. But let's do it. R phi d theta, right? So we have sine theta d the theta of that. So now it's going to be easier. It's going to be UQ d the theta sine theta. Let me just put this thing to the side. Sine theta dp d theta, right? That's the second term, right? And the last term, we're going to have this term here. Sorry for the mess. This thing is 1 over r squared sine squared theta. I forgot also in the previous one, but let's do that. Second derivative of UP, second derivative of Q relative to phi. Okay, so just to show how to explicitly do the calculation, and also so just notice that those two terms, this one and this one, both have the r square, right? So when you do these calculations like outlined, we're going to have something like this. Okay. After we rearrange and do the, you can show that gives this term. You can notice by seeing at the structure that we have a function that depends only on theta and r. You see u depends on r, and p depends on theta, so the whole thing depends on r and theta, right? And the second, the right hand side depends only on phi. And again, the same argument we used before, we have something that depends on two variables equals to something else that depends on a third variable. And they want to be equal whatever for any value of r theta phi. I'm not knowing what those functions are, okay? So the only possibility is that those functions are constants, okay? And let's assign a constant, m squared. The reason I could put an m, or I could put something else, or minus m, right? But I mean, if I use m, I would have a square root coming in all the formulas and all the equations and all the expressions. So it's more convenient just to use m squared. And also for physical reasons, for most classical situations, the sign chosen here is positive when the sign in this term is negative. So that's because we obtain a differential equation for Q that has periodicity. And it's very important to have periodicity in the azimuth angle, because after one turn, if you have the whole domain in the xy plane, if you have one turn, complete turn, the potential has to reproduce. Potential here has to be the same after you change phi by 2 pi. So that's why it's important to have this sign. But we could have combinations for some specific boundary value problems in which you didn't use that, right? It's not impossible. So we would have different results for the other functions. But most cases in which you have the whole domain in phi, you have that type of choice. So with the choice of the separation constant, and as I mentioned here, right, if you have the whole domain, this parameter m has to be integer. We didn't say anything about the possibility of m being real or not, or an integer. So m has to be an integer, including m equals 0. Also is possible, or positive or negative integer. Okay, so if the whole domain is included, which is in most situations we have, then we have m is an integer. So as we are going to see in a couple of pages, you know, the sign is going to be important if we use complex exponentials, as we will when we deal with spherical harmonics. So the solution for Q is combination of sine and cosine functions having m phi as an argument, or combinations of complex exponential for plus or minus j m phi. Okay, just a remark that I didn't do in the beginning of this course. We are an engineering program, electrical engineering. So we in electrical engineering use exponential of j omega t, okay, as time varying functions, for instance. So we use the complex the symbol j to say to represent the purely imaginary number. This is different from physics. People from physics, they use, instead of that, they use exponential minus I omega t. Okay. So we don't use minus I because that would change a lot of things in our methodology of all the other areas in electrical engineering. So we use J. The reason basically is because electrical engineers think about circuits, and circuits have current I, and they have phasors too of this type, right? So to avoid mixing those symbols, they change to J. And the sign doesn't matter. I mean, the sign we use plus, and let's keep using plus. So, but I mean, at the end, this sign is not going to be important. We could stick with using exponential minus I omega t as the physicists use, right? But to be consistent with our own field of knowledge, we are going to keep using j omega t. Plane waves, a forward plane wave, for instance, as we will see, is like something like this: exponential minus j kx. That means a wave that propagates along the positive x direction. So in space, we use minus jk to move forward, and in time use plus j omega t to move forward, okay, in time. So that's an important remark. Let's keep with that. What remains now for the differential equation is now to solve this equation here that we can when we assign this equals to m square, we have a second separation, right? We're going to have a part. I can extract the sine theta from here and put here. I can put sine square theta here, right? It's going to go also to the denominator here, but I can separate the theta part with the radial part. So I can do that. That's why you see sine square theta appearing down here, right? And you know, you have a sine theta divided by sine square, right? So we have, that's why we have this thing here. So you see that we have a function of r and one function exclusively a function of theta. And again, the sum is 0, whatever values of r and theta. So it means that each is a constant. H is a constant, and p, little p, okay, lowercase p, is a constant. For convenience, we are going to label the separation constant involving the radial part. We're going to assign this constant. I could put just a constant, a square, minus a square, or minus a. But because of the significance of the meaning of this parameter, we already anticipate just choosing the constant conveniently. So we have one differential equation, which is easy to show. You see, you're going to have a second derivative here. Then we multiply by u and divide by r squared. And we move this to the left-hand side. So you're going to have the simple differential equation, a radial differential equation. And for the theta differential equation, we have something like this. So we're going to solve those. I mean, we solved already the equation for phi, for the azimuthal variation. And that index was transported to this equation, right? Came back to this equation. So we have two equations, and notice that this one depends exclusively on L, and this one depends both on L, right, and on the square of m. Okay? So it means that a solution that I obtain here, if I change the sign of m, it doesn't change the solution. It must be the same solution, right? Because m squared, for instance, for a given index m equals plus 1, we have a solution. The other one, for m equals minus 1, must be a copy of this first solution, right? They are not independent, okay? So let's look at this one. This is easily solved by using a Frobenius technique, in which you assume, for this case, is enough just a single power of r, okay? So let's assume r raised to the alpha. So that's what we get. I mean, if we solve it, we're going to have alpha equals minus L plus L plus 1. Let's do some algebra here to see how it goes, right? So the equation is something like this. It's not easy to see that a single power of r solves the problem, because here we have the second derivative, and here we have the function divided by square of r, right? So if you assume u equals r to, I think I'm going to use a different symbol here. Let's see. Well, let's use alpha. That's okay. R to raised to alpha. So du dr equals to alpha r raised to alpha minus 1, the second derivative, equals to alpha minus 1 r raised to alpha minus 2. So when we plug that back there, we're going to have alpha minus 1 r alpha minus 2 minus l plus 1. Again, r raised to the alpha, right, divided by r squared is r raised to alpha minus 2 equals 0. Then we factor out r alpha minus 2, and we have equals 0 for any r, positive r, right, which is the domain of the function. So that means that we have alpha so one possibility is to use alpha equals to L plus 1. If you plug alpha equals L plus 1, you have L plus 1 times L. Okay, right? The other is to use alpha so that this gives L plus 1. So use alpha equals minus L as a second possibility. Minus L times minus 1 L plus 1 equals to L plus 1. Okay. So the two possibilities for alpha, there are two independent solutions, right? One is r raised to L, if L is positive, right? And the other, let's assume L positive number. We're going to see that it is. And the other is a negative power of r minus L plus 1, right? So so we see that this is the general solution. We still don't know what L is. It's an eigenvalue that will be determined. And notice that we have, meaning that we have phi, r phi equals to UPQ, right? So in fact, to find the potential, we need U over R. Or maybe I did something wrong here. L plus 1 and minus L. Let me see here. I think I did it wrong. Yeah, that's right. So this is correct. This is correct. Okay. So that's what we got, right? L plus 1 minus L, right? That's I thought I had done something wrong. So if we do this thing here, so it's going to UPQ, right? So it's just divided by R, and this one here, divided by R. So you're going to have R raised to the nth power for the potential function, and the negative minus L plus 1 power, okay? So that's the solution for the radial function. Well, solution for the angular function, this solution is conveniently obtained by doing a separation, doing this changing variables. I mean, I'm sorry that I have this ambiguous notation. I mean, this x might be mixed up with the x of the 3D space that we use, right? I should have used u, for instance, here instead of x. But I mean, since the class notes are like this, I mean, let's make sure that we understand that this x is not the x coordinate in 3D space. It's just a variable as a function of one variable x. Okay. So we do this changing variables. So derivative relative to theta equals d dx times dx d theta, which is minus sine theta d dx. And sine theta is 1 minus x squared. Let's look over the domain here, right? As theta goes from 0 to pi, x goes from 1, which is the zx, cosine 0 is 1, value of x, the variable x is 1. Theta equals pi, the variable x is minus 1. Okay. So you see that we can also play around with this. The operator ddx can be written as minus 1 over sine theta. It goes here, right? dd theta, right? So when we see in the differential equation 1 over sine theta dd theta, we just put minus ddx, right? And also, I mean, here dd theta equals sine theta ddx, so that's going to become sine square, right? Sine times sine square, and the ddx, and sine square is 1 minus x squared, right? And here we're going to have, instead of this, 1 minus x squared. So we parameterize the differential equation entirely in terms of the x variable, and it becomes the classical, well-known, okay? not well known by many of you, but I mean well known by others. Others know this equation. Mathematicians certainly know, right? So this is not us. We are just pure mortals. We don't know that, you know, we don't have that intimacy with this equation, but we know, right? So so this is the generalized Legendre differential equation. And notice that for m equals 0, what does it mean? M equals 0 means that no variation with phi, with the third coordinate, so it means azimuthal symmetry, right? For m equals 0, we have problems governed by functions that we know a priori that depend only on r and theta. So this is one class of problems. We are going to see a couple of those. Okay, and for m non-zero m, then we have the full dependence of the potential with 3 coordinates and spherical coordinates, right? We are going to start by looking at the problems having azimuthal symmetry. So the generalized Legendre equation becomes the simplest Legendre equation, which is that simple structure here, and that can be solved in a rather straightforward way using the Frobenius technique. Right? Look at the Frobenius technique in ARFCAN. Okay, go to the page, to the reference to words, and find Frobenius method. It's going to be there, right? That's the method that they also explore in their book. So it's assumed that the function p is a polynomial of x. I mean, that's a reasonable assumption, right? We can expand any function, any analytical function, as power series of the variable, right? So it's very reasonable that we assume that the solution is a power series. And we try to identify what type of power series we obtain. So you see how it's written here. The way it's written, I mean, this alpha is another alpha, has nothing to do with the alpha using the radial solution. So it means that the terms of lowest order, x to j equals 0 is 1, right? The lowest order is a power of alpha. If alpha is 0, is just the lowest order is a constant. Otherwise, it's gonna. I mean, the polynomial is going to start at x raised to the alpha power. Okay, so you just plug that inside. You're going to have rewrites like this, and we're going to. Going to insert this into the equation and rearrange terms. Okay, and when we do that, I mean, that's for you to do. Okay. So that's you are the one that needs to practice those need to train, you know, the working out those equations. So you go there and find that after you have to redefine indices, have to relabel indices so you can arrange terms of equal power together. After you do that, you're going to have something like this. Okay, so I can formally represent the result after doing all the derivatives and so forth. We're going to have a constant that depends on the index and on alpha, multiplying the power series equals 0 for any value of the variable x. So the only possibility of you having power series, which is 0, for any x is that the coefficient goes to 0. So find the coefficient yourself, the C of j alpha, this coefficient here, okay? And after we do that, we obtain several, three conditions. Recall, those coefficients are A0, A1, A2, etc. So we find the relationship between coefficients. We find one of the relations is this one involving exclusively A0. The other one involves exclusively A1. And then I mean, if j is larger than 1, then you have a general recurrence relation, which is this one here. Okay? So I have that recurrence relation. So just look at the structure of this, okay? The coefficient at j plus 2 is related to the coefficient at j, right? For instance, if for a given j equals to capital J, aj is 0, right? So if you have aj equals 0, it means that all remaining coefficients are 0. Okay. So for instance, suppose that I'm not solving nothing yet, right? I'm just saying, suppose that you solve for A0, so you can find A2, A4, etc. Suppose you solve for A1, then you solve for A2, A4, etc. Okay. Also, because of this, also we cannot have both coefficients equal 0. If we do that, we don't have any solution. The solution is the trivial solution. If we play around with this thing, you can choose, for instance, you can have one possibility, A0 equals 0, A1 not 0. You cannot have both of them. Okay, suppose one of them is 0. So, for instance, look at this one. If A0 equals 0, and if A1 is not 0, right? You have to have alpha equals 0 or alpha equals to minus 1. Because in this way, I mean, here alpha can be any because A0 is 0. Okay? But in this one, because A1 is not 0, if you have A0 equals 0, A1 not 0, then you have to have either alpha equals 0 or alpha equals to minus 1. Alternatively, if you have A1 equals 0 and A0 not 0, right? Then you have to have alpha equals 0, which is the same as the other condition, or alpha equals to 1, okay? So these conditions are equivalent, right? So in final analysis, we can choose either one different than 0, and we are going to obtain the general solutions that we are looking for. So let's choose, for instance, A0 not 0 and A1 equals 0. So one possibility is alpha equals 0. So recall that alpha is the lowest power of the power series, right? Alpha equals 0 means that the power starts at the term x raised to the 0 power. Then you are going to have, because A1 is 0, you're going to have A0, A2, A4, etc. So you're going to have x raised to the 0 power, x to the second power, x to the fourth power. So if I make the first choice alpha equals 0, we have an even function, right? We're going to have an even function of x. If I go to the second possibility, it means that the lowest order power is x raised to the first power. And obviously, you're going to have coefficients that are related in steps of 2. Okay, you have only odd coefficients, right? And you're going to have px as an odd function. So that's what we have. I mean, considering A0 not 0, we're going to have either this sort of situation here, even powers of x, starting at x raised to 0, or the other solution is odd powers of x. In other words, the two solutions, the two situations, and the choice of alpha determines the parity of the solution, okay? That's an important consideration that we have to examine. And we look for large indices, j much larger than 1, okay? So the relationship between coefficients, neighbor coefficients, is a factor like this one, okay? So for j very large, you can neglect everything that is summed to j. This is neglected, this is neglected, this is neglected, this is neglected, this is this, and this. So you're going to have j squared divided by j squared, which equals to 1, right? So you see that in this case, aj plus 2 for large j is approximately equals to aj. So for j very large, aj plus 2 becomes the same as the j. Okay? The ratio is 1, right? Now look what is the consequence of this. Let's calculate p of 1 or p of minus 1 for we know P of 1 is the sum of the coefficients, right? So we have a sum until a certain point, a certain larger number k, and beyond that, all the terms are equal. So we can factor out the last coefficient, multiply by 1. So I have a sum of 1 from k equals to k capital plus 1 to infinity. So it means that the function diverges at x equals 1. Right? If we're talking about a problem governed by Laplace equation, and there's no singularity in the z-axis, x equals 1 is that equals 0, it means that something is wrong here. This solution cannot be employed if we keep all the terms, right? It's unphysical. Same thing if you go to the minus z-axis. If you go to x equals minus 1, you're going to have, the only difference is that you're going to have a minus 1 in front of the sum. And this is diverges, right? So, P of plus and minus 1 diverges because of this property here, right? So we have to think about that. We have a mathematical solution, but to be a solution to a physical problem, we have to make sure that the solution works also in the z-axis and minus z-axis. So the only possibility for convergence is that we truncate the series. The series terminates, right? So that's the only way we can do a physical solution. We have to stop the series. So we have to make sure that we have indices to a certain point, and beyond that point, all the remaining indices will be 0. So how do we do that? So we have to find a number, capital J, okay, either for alpha 0 or 1, right, to stop the series. So the AJ is the last last coefficient, sorry. So this one is different from 0, but AJ plus 2 equals to 0, right? How do we do that? Just look at this expression here. So that's the last, that's the expression for AJ plus 2. So to make it 0 for a given capital J, so it's just a matter of making this numerator equal 0, right? And we have, recall that we have two possibilities for alpha. Alpha equals 0, alpha equals 1. For alpha equals 0, you have to use that in here, right? And here, alpha equals 0, you're going to have J plus 1 equals to L plus 1, right? Notice that J is a positive number, a positive index, right? So, solution, J equals to L, right? So recall that we have even powers, right? So we're going to have a 0 x to the 0 plus a 2 x to the 2 plus etc. plus a L x to the L. So it means that L is integer, right? And in this case is an even number. So one solution, the solution for index L even is a power series of even powers of x. If we do the same thing for alpha equals 1, okay, we obtain this type of thing here. So just make J equals L minus 1 to satisfy this equation here. Okay. Recall always L is an integer. Also is because J is an integer, right? So recall that index is not power of x, right? Index is J, but the last index is L minus 1, and the x to the L power. So in this case now L is, this index must be even, means that this, of course, this is odd. So we have odd powers of x, and L is the index. Okay, we are labeling those polynomials PL of x. When L is even, we have an even function. When L is odd, we have an odd function. So the parity of PL is set by the parity of L, right? Sorry. So this is just a quick example. Let's say alpha equals 0. Let's make L equals 2. Let's truncate at J equals 2. So it means that AJ plus 2 is we're going to go up to A2. So AJ plus 2 equals to this thing here. So we can calculate A2 for J equals 0, right? So it's going to be, let's do here, J equals 0, this is 0. L equals to minus 2 times 3. There's some mistake here, I think. Is this right? Well, this is 0 plus 1 times 0. So this term here doesn't exist, okay? Yeah. Yeah. This thing is right, but this thing is wrong. Okay, so we got, for A2, we're going to have minus 2 times 3 divided by 2, right? Like this. So A2 equals minus 3A0. And A4, I'm going to just erase the whole thing here again. A4, so this has to be thrown out. This is minus 3, this is right, minus 3A0, A0, right? And A4 and so forth is 0 because we truncated at J equals 2. So we obtain the polynomial at L equals 2. So that would be the structure of it. I have this constant here that can be calculated. So we have some, these are called the Legendre polynomials. And we choose the constant, the coefficients. You see that once I calculate A0, all the other coefficients are determined. So, by convention, we set the Legendre polynomial at x equals 1 equals to 1 always, right? So, if you do that, for instance, for P2, we can calculate A0. A0 would be minus 1/2. So the Legendre polynomial P2 would be something like this. So you see P0 is just L equals 0 power is 1. P1 equals to x. Because, why? Because it's just one single power. P1 of x equals to A0 times x. But P1 of 1 equals to 1. It means that this is chosen equals to 1. P2 is given by this one expression here, and so forth. Let me show you some polynomials here. Let's go to my Mathematica interface here. I'm going to show you some polynomials. just a little bits. Here. Let me see Legendre polynomials. Let's see what they are. They are here somewhere. Let me see if this thing works. Okay, we have here the Legendre polynomial. I can show a lot because I cannot show a lot of them here in my notes, but I can show you in Mathematica using this function manipulates. So you see P2, P3, and so forth, P4, right? And so on, right? So I can make a lot of polynomials if I want here. All the, I can, up to 20 here. I mean, I could increase that. If I put 100, I can have a very large, Legendre polynomial. Let's not do that, okay? Let's just keep it low, right? So here is a plot of different Legendre polynomials. This is the P0, which is a constant, okay? P0 is a constant. Then you go to P1 is the function, linear function, right? Then you go to P2 is the quadratic function. So you see that's an even function. P2 of 1 equals 1. P2 of minus 1 equals to minus 1. P2 of 0, well, in this case it's 0.5. You see that's very hard to calculate, but we have a general expression for PL of 0, which is going to be employed sometimes. But I mean, you see that because the function is odd, PL of minus 1 equals to minus 1 because PL of 1 is 1. Okay, so let's do some more. So you see that the Legendre polynomial have an undulation that is an attribute of orthogonal functions. I mean, a basic attribute. I mean, orthogonal functions, generally, they have undulations, oscillations, right? Like the sine function, cosine function. And we have, you see, I mean, the function is bound at x equals 1 and keeps oscillating, right? I mean, increasing lobes and more lobes as you increase the index, right? So I have several Legendre polynomials. So it's already a hint that we are going to be able to make expansions using these functions, right? Because they definitely, if we're going to examine in more detail the Legendre equation, it's governed by an Hermitian operator, and it generates the eigensolution are orthogonal if you define a domain like this one, minus 1 to 1 for x, right? In this domain, those functions have orthogonality. They have the definite orthogonality properties, okay? Let me just close this thing here. This is a plot that we have in our class notes. Okay, I'm going to show some curiosity of those things. What else we have here? We have a couple of properties. We are not going to demonstrate. I mean, some of these demonstrations, they require understanding how to play with differential equations. It's not our scope in this course to do that. But one interesting formula is the well-known Rodriguez formula that allows you to generate Legendre polynomials by using this L-order derivative of x2 minus 1 raised to the Lth power. Okay, so that's, I mean, we are not going to derive that. That certainly was a paper by this fellow Rodriguez to demonstrate this, right? I mean, it's not that simple. As I mentioned to you, we have orthogonality of those functions. So if you have a function running on different indices, they are orthogonal, right? They are not normalized because the criterion here was to attribute PL of 1 equals 1. Because of that, we cannot normalize the scalar product. But I mean, the scalar product has a definitely very well, very well established normalization constant, which is 2 divided by 2L plus 1. So this is the Kronecker delta. So it means that I can expand a function in the domain, let me just fix this in here. Magnitude of x smaller or equal than 1. In other words, 0 is more than theta is more than pi, right? In the domain 3D space. It means that this variable here that we are using, x, is limited to 1. So, I mean, the properties, the scalar product is like this, right? Now, in our symbol, remember also, PL are real functions. They are not complex functions. So, I don't need to put a conjugate here in the definition of the scalar product, right? So, it's not required because the function is real. So, we have... we can expand any function as a linear combination of Legendre polynomials, and applying this, this orthogonality property. If I make the scalar product on each member, right, L prime here, so this is going to be PL prime, PL. So this is delta L prime times 2 over 2L prime plus 1. So that isolates, right, the L coefficient. So we could determine easily, I mean, just knowing that property, right, we determine the L coefficient in the expansion. So in practice, this is a symbolic calculation, but in practice the calculation is carried out using this formula here, which is the integral of x times PL from -1 to 1, right? Let me just show you here. So the L coefficient equals to but in the physical domain, fx is a function of theta, right? It's not this. X. In fact, it's a function of. You can put the function of theta. It's okay, right? And PLX is a polynomial in which the powers of cosine theta, right? The largest power is cosine theta raised to the nth power. So if we use x equals cosine theta, make a change of variables, the x equals minus sine theta, the theta, right? X equals -1, theta equals pi, x equals 1, theta equals 0. So here, this is going to become integral from pi to 0, the x is minus sine the theta, f theta, PL cosine theta. So this is, I can reverse the indices do like this. I forgot, yeah. The theta, sine theta, PL cosine theta, f theta. So I have to do this integration. In most situations, it's easier to parameterize in terms of the x variable, okay? Well, we have as any set of orthogonal functions, they have to be complete, right? So the completeness of the Legendre polynomials is established by this relationship. I mean, the only reason we have this factor is because they are not, the scalar product is not normalized. So you're going to have, otherwise we would not have this factor here. We'd have only that one, right? So we have that factor here. Let's see completeness, how it works in practice, right? Let's just close this one here. Let's look at the completeness. I hope I can see it here. So we have here the formula, right? I mean, you can see, you can identify here 12 plus 1 over 2, Legendre polynomial, right? I'm doing two different Legendre polynomials. I don't know why it's like that. Well, maybe this is wrong. Let me see here. Just a second. Oh, okay. So this is right. This is right. This is Legendre polynomial x equals x, x prime equals 0. Okay? You can see here in the function. So let's do some calculation here. Let's start. This is including. I'm summing, looking at the formula that I just showed you in my lecture notes. So I'm going to increase the number of terms in that completeness relation. I'm truncating at n equals 0, n equals 1, n equals 2. I don't know why it's not calculated. N equals 3, n equals 4, 5. I hope it's calculating correctly. I think it is. So I'm going to increase the number of terms to see how the completeness, it means that as I increase the number of terms, that sum has to become a delta function, right? You see, it's taking some time to calculate. It's not being too fast. You see that as I add more and more terms, we start to have a resembling peaked function at x equals 0. It means x prime equals 0, right? It takes a lot of terms until we can see it. I'm going to increase faster, a little bit faster. You see that the peak value is increasing, right? And the width is decreasing. So we are concentrating more and more. For the 80 terms, it's calculating, still calculating. Right? It takes some time. You have to put a lot of terms so you really get to the delta function, right? I'll try to make 200 terms here just to see if it calculates. I hope it doesn't blow up my computer. Let's try to put 200 here. It did 100, right? Let's put 200 terms. See what happens. Still doing. Well, let it go. Oh, it did. Okay, it's getting nicer, right? The delta function is just something that's concentrated. It doesn't have to be a beautiful, smooth function like this, right? It means that if you make a product of this function with something that grows smoothly, right? And then if you integrate that, it's going to be effectively the value of the function that changes smoothly at the singularity point, times the integral of this function, whatever shape it is. So, and the integral is normalized to 1, right? That's the idea of the delta function. It's just any function, any shape that has an even function behavior that has a peak in which the width is inversely proportional to the height, so that the area is constant. That's it. You can use any function to approximate to a delta function, right? So, so I have some important relations here, which are useful in calculating integrals involving functions product with Bessel functions. If we use, sometimes these properties allow you to calculate integrals much easier. You can find those properties in Rifkin when it treats the Legendre polynomials. Okay, these are general properties of those so-called hypergeometric functions. They have similar properties, similar recurrence relations. Okay, this one is an interesting one, and so on. Okay, just gonna write that down without demonstration. So, in summary, we have the general properties of the functions. We understand how they are. So let's see a solution of a boundary value problem having azimuthal symmetry. So those problems can be, the solution is going to be cast as the product of a radial term, right? Because we know, by symmetry considerations, we know that the function depends on r and theta. Then we can write a general solution like this, right? That's the general form of the radial function, and that's the Legendre polynomial. Remember, every time I have a power of r raised to L, I have to attach to that power the Legendre polynomial of order L. If I have a solution that has r raised to minus L plus 1, I have a Legendre polynomial of order L. Has to be attached to it, okay? For instance, suppose that you know that the solution is like this. R raised to the first power, P1 of cosine theta, right? What is the solution? Well, this is R times, well, P1 of x equals to x, and x equals cosine, so this is R cosine theta. But what is R cosine theta in 3D space? Simply z. So this is a solution in which the potential is linear with the z coordinates. Obviously, second derivative equals 0, right? Satisfies Laplace equation. Right? So that's just an example. So every time we have an L here, we have to have a PL there. If we have r raised to minus L plus 1, we have to know what number is this to attach to it PL cosine theta. Right? You don't have a solution that has r raised to L plus 1 without a change in relative to the theta variable. It has to change in that prescribed way. Okay? So let's consider this situation in which we have boundary value problems with azimuthal symmetry. In this case, we know a priori that the potential depends only on r and theta, and because of that, and because of the structure of the solution for spherical symmetry, for spherical boundaries, the solution is going to be in this form, right? So let's look at this type of problem governed by this equation here. Just erase this thing here. The potential, I want to determine the potential either inside or outside of the spherical region, given the potential at the boundary, right? So you have the interior problem and the exterior problem, right? So the general solution is something like this. I mean, this general solution can be expressed in this form. I'm going to show you how, okay? Because, I mean, you see that the general solution is something like this. I mean, that's the way we express, right? Try to solve the problem. So you see that for the interior problem, there is no singularity in the origin, so there can be no term that blows up at r equals 0. So for the interior problem, we have BL equals to 0. And for the exterior problem, we have, I mean, assuming that potential vanishes for r very large, then I have to set AL equals to 0, right? So for r smaller than a, the general solution is on the form and for r larger than a, the general solution, I mean, the solutions are independent, right? Because given the boundary, the solution outside, whatever happened inside, is going to be given, right? So it's going to be sum right? So, I mean, before we calculate the coefficients, notice that those solutions, they are equal at r equals a, because they are equals to phi, right? The function of theta I mean, the solution has to be exactly the same in the boundary. So r equals a goes minus L plus 1 here. PL cosine theta. So what does it mean? Because this expansion is unique, this coefficient has to be equal to that one. What does it mean? I mean, if I calculate one of them, I have the solution for the other one, right? So, for instance, AL raised to AL equals to BL a to minus L plus 1. So BL equals to AL a raised to 2L plus 1, right? You can do that. So if I write the solution like this, AL prime R raised to L divided by A to L plus 1, and I could put here BL prime, right? And I put here A to the L divided by R raised to L plus 1. If I make this change, right? I just make a little change. You notice that the structure of this ratio here is the same. Is the L power in the numerator and the L plus 1 power in the denominator, right? The only thing that we invert the position of R and A, right? So what happens now? Let's equate the two things. So at R equals A, this is going to be 1 over A right? So this is going to be AL divided by A. And in this one, at L, R equals A, this is going to be 1 over A also, right? Right? So in this case, I have a symmetric property here. So because those expansions are equal, AL over A equals to BL over A. In other words, by doing this change in the coefficients, I have a symmetric property, AL equals to BL. So what happens here, for R smaller than A, I have the smaller between R and A on top, and the larger on the denominators. So if in this case, the smaller between two values R and A is R, the larger between R and A is A. So for the interior problem, I can call the smaller R is R, the larger R is A. For the exterior problem here, the smaller between R and A is A, and the larger between R and A is R. So I can synthesize, right? These two solutions in a single one. This general solution can be written as one single coefficient, right? A ratio between two parameters. One is the smallest distance raised to L. The other one is the largest distance raised to L plus 1. And here we have PL cosine theta. So that's the way to write the solution. It serves to inside or outside, interior or exterior problem. If you want to consider interior problem, smaller r equals to R, larger R equals to A. Exterior problem, smaller r equals to A, larger r equals to R. So I can put the two solutions together like this. The only thing that's left is to determine the coefficient, and now we go to the orthogonality. We propose using this type of solution, right? So at R equals A, we have this equals to phi of theta, or phi of x, if you want. Let's call it phi, equals to an expansion of, this is going to be 1 over A, right? Whatever larger and smaller are, right? Sorry about the mixed words here. 1 over R PL, right? Oh, sorry, times AL. So I make a scalar product, PL with phi, equals to, we're going to isolate a single parameter, right? Normalization. So we're going to have 2 divided by 2L plus 1. AL over A. This is already the PL with PL equals to 2 over 2L plus 1. So we have AL equals 2L plus 1 over 2A. And we have to calculate this integral. In practice, how do you calculate that? Integral from -1 to 1 of the x, PL of x, phi, or if you want, integral from -1 from 0 to pi of the theta, sine theta, phi of theta, or better, PL cosine theta, phi of theta. Right? That's the prescription. So the problem is solved whatever is the function that you have on the boundary, right? Let's make an example, practical example. We have this, let's assume that we have two spherical electrodes, one on the north hemisphere at plus V volts, and one at the south hemisphere minus V volts. So your function is some step function type. Potential equals to V in the south hemisphere, theta from pi over 2 until 2 pi, right? And it's positive on the north hemisphere. So it's a matter now on calculating that integral, right? Parameter in terms of x. So we have to break the integral in two. One is negative. The other one is positive. So we have the parity of the function. If L is even, for L even, this term cancels that one. So there's no even coefficients. For L odd, you have this integral is minus the integral from 0 to 1. So we have twice. So we have twice. I mean, the 2L plus 1 over 2, the 2 cancelled. So, I mean, so here is, I mean, the calculation is based on the recurrence relation. So it becomes easy to calculate, okay? So it means that PL can be expressed in terms of derivative of neighboring polynomials. So the integral of the derivative yields the polynomial itself. So it's left for you to calculate that, right? Use the recurrence relation to calculate this type of integral here. So we have a little problem here, which is to determine I mean, when you do that calculation, you're going to have to calculate PL minus 1 of 0 and PL plus 1 of 0. L is odd, right? So PL minus 1 is index is even. If the index was odd, this would be 0 because the parity of the function. So I have to calculate that, and it's doable, but it takes 2 or 3 pages of my lecture. So I'm gonna leave it also to you. I mean, those hard ones, you can. I give it free for you, okay, to calculate. So I can show that the polynomial Legendre polynomial at k in the origin is only non-zero for k even, for k odd equals 0, right? And it's given by this funny expression here, minus 1 raised to k over 2, which is can be even or odd, right? And you have this double factorial functions, which by definition is a factorial in which the numbers jump in steps of 2, okay? So k factorial is 1 times 3 times 5 times 7 as for odd k, right? Or 1 times 2 times 4 times etc. if k is even. Okay, so that's the result. So we have the result for the interior problem or the exterior problem now expressed here in my notes. Okay, So just demonstrate that with the algebra. Okay. One very nice, the power of orthogonal functions can be used, to find solutions in very simple fashion, One such technique is giving the solution in a subdomain. In general, the subdomain is, for instance, suppose you solve a potential problem in the z-axis, right? And the function is separable in spherical coordinates, and the function of two variables, r and theta. So we know that the general structure of the solution is like this, right? So what happens in the plus z-axis? Plus z-axis, theta equals 0. R becomes z, right? And PL of 1 equals to 1. So the solution, the general solution becomes this function of z, which is a power series of z, positive and negative values, right? So what is the approach of solving problems in more general way? Suppose you find a way to determine, by integration or by other methods, the solution for the potential problem that you know that depends on r and theta, right? You find the solution in the z-axis. So what you pick up, you expand the solution in a power series, and you collect the z to the l and z to the minus l plus 1 terms together, right? So what happens? If you want to find the general solution, you just change back z to r, and each term r raised to l and r raised to minus l plus 1 has to be multiplied by PL cosine theta, because that's the structure of the solution. So it's a very simple approach to solve problems. So the only difficulty is to expand the function, right? Generally, use a Taylor series expansion to do that. I'm going to give you some examples that we didn't solve before. We solved for the ring of charge, circular loop, a charge line, circular charge line, with a constant charge density, radius a. We solved the problem in the z-axis before, right? We never solved the problem outside the z-axis, in this region here, right? No, only on the z-axis. In the z-axis, it's very easy to solve for the potential. This point is always at the same distance of any point on the ring. So the potential for a given point or given charge is the phi equals dq divided by 4 pi epsilon 0 times this distance here, which is, I'll put here, a square plus z square, 2 1/2. So if we integrate, is going to be the total charge, right? So that's the result we get. Simple to calculate, right? On the z-axis. Every point on the ring is at the same distance, equidistant from the point in the z-axis. So I have the result in the z-axis. What I have to do is to expand this function here, right? I have to expand the function. In fact, is 1 plus a square over z squared to minus 1/2, or equivalent is 1 plus u to minus 1/2. So what you have to do, this is equals to, let's call this f, right? This is f of 0 plus 1 over 1 factorial, first derivative, times u, right? 1 over 2 factorial, second derivative at 0, u squared, plus 1 over n factorial, fn, n derivative, u to the n power, right? So what you have to do is calculate those derivatives, f0 equals to 1. First derivative is minus 1/2, which is minus 1/2 times the function. So the first derivative is 1 plus u to minus 3/2 times minus 1/2. Right? The next one is going to be 1 plus u minus 5/2 minus 1/2 minus 3/2, and so on. And you can calculate this expansion, right? After you do that, you obtain something like this. You can notice that you have a double factorial here because you have 1 times 3 times the next one is going to be minus 5/2, right? You see that there are 2 squared, 2 to the cubed, 2 to the kth power, and you have a double factorial 135 here, right? So that's why we have this. This k factorial comes from the formula, Taylor series, and this 2 to the k is the 1/2 multiplied several times. You have that power. So the 2 here is because you have a square factor here. So that's the expansion, right? So we have to consider here when z is larger than a, you have one situation, and when z is smaller than a, right? So you have to use one solution. Maybe not, huh? Let me see. Yeah, I mean, you have to consider that this expansion, right? This expansion here is only valid for z larger than a, okay? Otherwise, I have to make an artifact. I have to do it different here. I have to do it differently. So the solution that we are doing here is for z larger than a, and obviously, if I find that solution, I can do that trick, r smaller and r larger. I can invert things. It's going to be the same result, okay? So if we find the solution for r larger than a, I can find for r smaller than a. So let's look at the solution, how it is, how it looks like here. So we made the expansion. Now, what do we do now? We just, next step is to replace z by r, right? And attach a PL cosine theta to the solution. So we're going to have a solution valid for any r larger than a, right? For now, r larger than a, because here a is on the numerator, z in the denominator. I think, oh, that's just expansion, right? So notice that when I did that, I put z outside here, right? So we have that expansion, and I have to multiply by z here, okay? So that's the result we get. I mean, that's the potential in the z-axis expanded. Notice that you have z to the plus 1 because we had the other z outside. It was factored out of that root square expression, right? We did something like this. Z times 1 plus a squared over z squared to 1/2 on the denominator, right? So this z here is this one. And this one here is from this power series there, okay? So that's why we get. So let's do now the technique. Change z goes to r and attach a PL cosine theta. So we're going to have this solution like this. So it's only even terms, right? Notice that we have a smaller r to the L power L equals to 2k, larger r raised to the L plus 1. If we want to solve the problem for r smaller than a, it's just a matter of inverting the position of those two guys here. So you're going to have r on the top and a in the bottom. The two functions are equal at r equals a, right? They have to be unique. That's a uniqueness of the solution, right? Well, one important topic in this development is the expansion of the inverse function. You have those Legendre polynomials that they have very nice properties, orthogonality properties, and you recall that the inverse function appears several places, right? Potential is going to appear in radiation fields, for instance, for point charges. You know, it always appears as the kernel of integrals. I mean, in the green function, we have the inverse function plus another function. We have a Laplace equals 0. So it's many situations important to expand this function in orthogonal functions. So we have a prescription for that. We can do that in terms of Legendre polynomials or other types of orthogonal functions. And the principle is based on this technique of solving a potential problem by knowing the solution in a subdomain, right? For instance, suppose that we have, the x and x prime vectors. They have an angle gamma between them. One is at r from the origin, the other is at r prime. If you make gamma equals 0, those vectors are collinear, right? Becomes r minus r prime. And what we do here, we use the same technique. Let's say that one is the z-axis, one of those vectors, right? So I have to expand this function here. So it has two possibilities. If r prime is smaller than r prime is larger than r, right? So we do this restructuring of this term. So this 1 minus a number smaller than 1 raised to the minus 1. Here's the same thing. Depends on the conditions, right? And then we can expand this very simply. This is a geometric series, you know. So we can make a general expansion using the concept of smaller and larger. You can always expand like this. Smaller r and the ratio between smaller and larger r. And this is very easy to expand, okay? So it can easily be shown. This is a medium high school can show that. This is a geometric series. Ratio. The ratio is this one. The sum is given by this, right? So when the vectors are parallel, you can expand in a very simple way. You see, I can now make n equals L, right? And now to find the general expansion for a gamma non-zero, you just multiply by the Legendre polynomial of that angle, which is in this case cosine of gamma. So that's a consequence, right, of the uniqueness of the expansion. So that's the way to expand the inverse function in terms of Legendre polynomials. And in this way, you can find, solutions using this technique, right? For instance, suppose you have a loop. Now place it at a certain height. You are at a certain height from the z-plane, from the z equals 0 plane, right? Have this loop there. You have a density constant. The loop, the ring of this loop here defines this angle alpha. And I want to calculate the solution anywhere, right? Well, what do? First, I calculate on the z-axis. Then I use the technique to find the general solution. On the z-axis, you can now use the inverse function, okay? At the point of coordinate z, defined by vector z, if you define a vector AC, a versor AC, the vector here is CAC, so the distance is the magnitude of this vector here, right? So we now expand that. Let's expand the inverse function. Angle between the two vectors, ZAZ and CAC, x and x prime in the previous example, is equals to alpha, right? So the solution is going to be, in terms of Legendre polynomials, given by this ratio, PL cosine alpha, right? R smaller, R larger is the smallest or larger between Z and C, because you see here, right? What you have is this. So that's the solution in the z-axis. To find the solution anywhere, just multiply the factor R, the Lth term, by PL cosine theta. Right? That's what you do. Right? So that's the solution we have anywhere for a loop that's not at z equals 0 as a function of r and theta. And always, you always notice this thing here. Okay? So you see that the two regimes are larger than R larger than in this case it's R larger than between R and C. So you're going to be R smaller is the larger between R and C, and smaller is the smallest between R and C. But you see that those two functions are equal at R equals C. Right? Calculate on one side is the same as calculate on the other side. Now, going a little quicker now, we're going again with the long lecture. I hope the upcoming lectures are going to be a little shorter because we're doing a lot of stuff in the beginning. Okay. As I mentioned to you, we have the time points of each subject, so you can skip parts that you already know. Don't have to watch the whole class, but you can watch the whole class, of course, but you can go to specific time points. So if you have now m different from 0, you have these associated Legendre polynomials that now depends on two indices. Okay. We still have L an integer, but allowed values of m are those between minus L and L. So we have also that criterion for convergence. We have several ways of calculating those polynomials. I'm not going to look at the in details of those. As I mentioned to you, the differential equation depends on the square of m. Because of that, those functions are not independent. So, one is a replica of the other one, right? So you see that now we're going to have some funny combinations of cosine and sine. Okay, I'm going to show you in a minute. When you have indices m different than 0, we have some. You have also still orthogonality conditions are a little more complicated. Okay. And again, we can always expand a function in the now remember, m different from 0 means that now the potential also depends on the third coordinate, on the azimuthal coordinate, right? Here we are just looking at the dependence on theta. When you have m not 0, the dependence on theta depends on indices L and M. M comes from the variation in phi, right? So we have those orthogonality properties for associated Legendre polynomials. And you can always expand a function in terms of Legendre polynomials. You see that you have different expansions here, right? For a given m, I have one set of coefficients. If I change m, I have another set of coefficients. I have several ways of expanding a function by changing the index m. Okay. So if we put together the associated Legendre polynomials and the azimuthal variation of the function, which is cosine and sine, okay, if we use those joint properties, that's one orthogonality condition. The other one is the complex exponentials, which are the solutions of the differential equation on the azimuthal coordinate, have this property as well, right? So we have orthogonality between complex exponentials. So we can define a more general function, which is useful not only here. It's going to be a complex function, but every time you have a real potential function, those complex functions combine such as you have a net result as a real function, okay? But those functions are very important also in quantum mechanics, in which you have a Schrödinger equation and the angular solution in general for central potential, for problems governed by central forces. You always have the solution, angular part is going to be spherical harmonic. So defining like this, with those normalization constant in front, you have this normal. This is so defined so that the harmonics, spherical harmonics, represented by YLM of theta phi, right? They have a normalized scalar product. So it's going to be delta L, L prime, delta M, M prime. Before I go to the spherical harmonics, let me go to the Legendre polynomials. Just to take a look at, I didn't have that one. Well, these are associated Legendres. A couple of those, let me just show you some of those. You see, these are associated Legendre polynomials you're seeing now, okay? P00, right? L and M are the indices. P00 is 1. P10, all of those are the standard Legendre polynomials. For m equals 0, have the standard Legendre polynomials that we have before, right? But now if you have an index, you see that you have x powers, right? But when you have an index, you are going to start to have functions of 1 minus x square root square, which is sine, right? So I have cosine square and sine, right? So we have that term, you see, to the 3 halves. So it's the third power of sine. So you're going to have minus 3 is the third power of sine, minus 2 is the, you see, is the square of sine times cosine. So it has sine to the third power, sine squared times cosine. Then you have sine and the cosine square. You see, you're going to have something that is sine to L, cosine to L minus M. Those powers you have. These are the combinations you have. You see, 1, 2, and 3. So we have, you see that this is minus 15, right? If I go to minus 3, oops, what the hell is that? 1 over 48. Oh, they are different. I mean, it's just a scale factor here, but the function is the same, okay? It's just a scale factor times the other one. You see, I mean, they are not the same, but they are replicas, one from the other. Minus 15, same function. 48, same function. And so on, right? You can go and calculate other functions. Let's go back here. Let me close that. Now we have again completeness of the solutions. I'm just not going to calculate that, not going to simulate the completeness of spherical harmonics because we have complex exponentials. Sometimes it might be funny the result, so we have to be careful in doing that. But we have, I mean, you can expand a function of angular variables in terms of spherical harmonics, and it's easy to calculate the coefficient as a scalar product. And have the completeness, right? Recall that this is 1 over the derivative, is one of the assignments in the homework, times delta of the difference of the angle. Okay. Let me show you a couple of spherical harmonics. I think I have that. Yeah. These are kind of you see, you have those things here, but I can show a lot of them in my Mathematica interface right there. Right here. Let me show you. Now you see that we have a normalization constant here, right? It doesn't allow me to calculate. I have to L equals 1, M equals 0, M equals minus 1. You have exponential, complex exponential here, right? M equals 0, M equals 1, and so forth, right? L equals 2, and have several. Unfortunately, the Mathematica is calculating the fraction here. I thought it was going to rationalize those numbers, but I don't know why it's doing that. But here you have several spherical harmonics. We have a symmetry property, which is very important due to the those things I'm going to ask you to demonstrate in the homework, okay? These are not difficult to show. Just go to the definition, the properties of the associated Legendre polynomials. You have this important property here, right? I mean, epsilon y, capital Y, epsilon, capital Y of L minus M equals to minus 1 to the mth power conjugate of Y L M, right? So you have these properties. So you see, I mean, when you have solutions of Laplace equations, those things combined, you know, the indices plus and minus combined so that you're going to have a combination yielding real functions. So that has to happen, right? Let me show you some plots. I mean, because these are complex functions, I'm picking here the real part, some, some spherical harmonics. You will recognize that the course logo is one of those. I mean, it's not here, it's a more complex one, right? The one that you see on the screen is one of those. So these are the distribution in space. You will see that the orbital electronic cloud in atoms resemble these plots, right? Plots that are similar to those, orbital P and so on, right? It looks like this. We have also to modulate with the radial variation of the wave function. So we don't have that here, just have the angular distribution. So the solution of Laplace equation now assumes the form when you know a priori the function depends on 3 coordinates. That's the general way of writing the solution, and it's easy to calculate the coefficients, right? Because we use the scalar product property. To conclude this lecture, I'd like to talk about the addition theorem. I mean, we expanded the inverse function in terms of Legendre polynomials, right? Like this one. Now we want to find a general expansion of the inverse function in terms of spherical harmonics, because I mean sometimes you have to calculate things. For instance, when you want to calculate the integrals involved the inverse function, if you expand it in terms of spherical harmonics, you use orthogonality properties. So it's very important to do expansion. When we talk about expansion of the inverse function in terms of spherical harmonics, this is called the addition theorem. Okay, so it says that essentially that PL cosine gamma that appears in the sum here can be written in this form. Okay, so if that is the case, if we insert this expansion in here, you have the structure, the formula that gives you the addition theorem. You have 2 vectors, x and x prime, right? You can show that the inverse function can be expanded like this. What we have here, right? I mean, you have to know which one is larger in magnitude, x or x prime. So you're going to have to put the smaller on the numerator, raised to L, and the larger in the denominator, raised to L plus 1. And here you're going to have the spherical harmonic conjugate calculated at the angle theta prime phi prime subtended by x prime. And you're going to have the spherical harmonic calculated theta phi, which are the angles subtended by x, right? That's essentially the that's the addition theorem. I'm going to go to the proof, okay, of this, because Jackson doesn't have a very simple proof. It's just an argumentation, but it's not very simple to follow. I have a clearer way to prove this addition theorem. I like to go through this proof because it shows the power of expansion of functions in orthogonal functions, the power of orthogonality of functions, and using those concepts, it's easy to demonstrate this. So it takes some considerations that are important. We are going to review some properties of spherical harmonics during this demonstration. First of all, we have demonstrated before that the inverse function, right, can be expanded in terms of Legendre polynomials of cosine of the angle between those two vectors. We are not talking about theta and phi and theta prime and phi prime, but the angle between them. Okay. We can also expand the same thing. I mean, this is a function of theta and phi. We can also expand as a function of spherical harmonics. Okay. We're going to have a coefficient. We're going to have a ratio as smaller and R larger. And this coefficient here is going to be a function of the angle subtended by x prime. So these are supposed to be constant, but in fact they depend on the arguments of this function. So you notice that, I mean, but uniqueness of the two expansions, this one and this one, you can identify that the term here must be equals to this term here. That's called uniqueness. There's only a way to expand it. If those two things are equal, it's because this function here is equal to this expansion here, right? So that's the first outcome in our proof here. PL can be written as a combination of spherical harmonics. Because this is order L, I can only use the same order of spherical harmonics. You know, because those have a cosine raised to the L, cosine raised to L minus 1, sine raised to 1, cosine L minus 2. So I can only use up to the power of L. So that's why we have this result. I mean, order L, I mean, that's uniqueness of expansion, but at the same time, you see that it makes sense, right? This is L powers of cosine of gamma, and cosine of gamma is a function of theta, cosine theta, sine theta, and so forth. So we have to use the same indices here, right? Coefficient of ALM can be determined by using orthogonality. You know, I make a product with the conjugate, make a scalar product on both sides here, and uniquely determine the coefficient ALM, right here. This integration is done in the theta phi domain, right? Now I'm going to make a change of variables. Let's look specifically in x and x prime. You see, I mean, I'm going to try to show you. X is the system of coordinates. Make a different color here. X is this system of coordinates here, right? Let's assume that x is the vertical axis, right? X prime. So x is obtained from x prime by rotation, right? We first we can let me just draw here, right? What I mean is like changing from rectangular coordinates to spherical coordinates. What happens is that we make our operation have x, y, z. First, we make a rotation of 5 radians. So you still keep the same axis, okay? So the new system, x prime, y prime, this is prime are not related to the x prime in the demonstration, right? And now I make a new rotation and go here. Using this axis, orthogonal to this axis here. So I have the new vector. So that's what I did. I mean, we have here. I don't have to worry about those axes, but I mean, I had x. I made a gamma rotation, right? And also a beta rotation. So beta has the role of phi and gamma has the role of theta, right? So you have x prime, then I produce x by doing this. So x and x prime have an angle of gamma, but I mean, if I want to look at the two different coordinate systems, x can be is depend on theta or phi, and it can also depend on gamma and beta, right? So if we look at the picture here, I mean, this integral is being done in theta phi space, but I can change the integration to the gamma beta space. I mean, remember gamma is like the role of theta, and beta is the role of phi. Okay, so theta is going to be a function of those angles, those rotational angles that I just showed you, and phi also will be. I mean, the solid angle is unchanged by this transformation because it doesn't change. It has, if it's 0.1 star radians, it's going to be 0.1 star radians in any system. Okay, it isn't changed. Okay, so when I do that, so I have this, I mean, I define, right? I define this function as a function of gamma and beta. I mean, the YLM theta phi, if I parameterize in terms of gamma and beta, it's going to be a G of gamma beta. So the coefficient, the special coefficient, right, can be written like this. Right? But notice that the function g, which is this one here, let me just erase something here. This function g is a spherical harmonic of order L, and as such can be expanded only using the same set of spherical harmonics. Okay, if this function is a function of gamma and beta, my spherical harmonic is going to be a function of gamma and beta. You're going to have these coefficients, right? And then I can calculate this coefficient, again, using orthogonality, integration gamma beta space, right? Now let's look at this coefficient at m equals 0, right? I'm going to set m. So you see, I mean, you have two things here. I have this coefficient here, which I don't know. I want to determine ALM. Why? Because I want to determine this exponential here. I want to know who is ALM, right? So I'm doing some tricks here, right? I made a change of coordinates. I redefine the function now in terms of these new coordinates called G. And again, ALM, the same thing here, is now written like this, integration in gamma beta space, right? So again, because G is harmonic spherical harmonic of order L, it can only be expanded as a function of those harmonic spherical harmonic of order L. And I can calculate this by doing the scalar product again, okay? Right? So let's look at, I mean, the m equals 0 term. Let's set here m equals 0. Now the properties are going to be used, right? So B0 specifically is YL0, right? It's the same expansion. I just made m equals 0. It's going to be L equals 0 here. But notice that YL0, that's a property of spherical harmonic, right? When I have m equals 0, it's going to be something like this. It's given by this expression. Doesn't depend on the azimuthal coordinates, only on the polar coordinate, which in this case is gamma, right? Because I'm doing relative to the space. So B0 is given by this expression here. So that's called 3i. So look at the class notes, okay, lecture notes. Compare 3i with the, you see the structure here in the integral with the expression for ALM, which is exactly the same, unless of the factor here is 1, and here is 2L plus 1. So if you compare those two, it shows that B0 equals to 2L plus 1 over 4 pi times ALM, root square, right? So if you go again to the expansion, go back again here. Let's make now gamma equals 0 on both sides of the expression, right? Because you see, I have B0, I don't have BM. So I'm going to make gamma equals 0. So I'm going to have YLM of gamma equals 0 beta. But there's another property, which is very interesting. If I make gamma equals 0, I have this sum here. I only know B0, I don't know the other BMs, right? So for gamma equals 0, it has to be a combination, but for gamma equals 0 here. But on the other hand, for gamma equals 0, YLM is going to be 0 for M not 0, and it's going to have a value PL of 1 times this factor here. That's nice, right? So YLM independent of M different from 0 is 0, M equals 0 is going to be this factor here. So this in fact is only one term, which is B0 times this factor. So you see that G gamma beta for gamma equals 0 equals to B0 2L plus 1 over 4 pi. Why is this important? Because I know I have a relationship between B0 and ALM right here. So this is known, right? Recall, I want to calculate this guy here. If I know B0, the problem is solved, right? So what I'm showing is that G gamma beta for gamma equals 0 equals to this multiple of B0. And what is G gamma beta of gamma equals 0? Well, in fact, right, going back to B0 and relating it to ALM, we have that this is proportional to B0. We have that factor, so we have ALM as a function of G gamma beta for gamma equals 0. But what is G gamma beta for gamma equals 0? Sorry. Let's go back to C here. What is C? We C here. Well, look at this. For gamma equals 0, this is going to be, the vectors x and x prime, x equals to x prime, right? So it means that theta equals to theta prime and phi equals to phi prime. So G of gamma equals 0 is YLM conjugate, calculate that theta prime and phi prime. So then we have what we were looking for. ALM equals to this thing here, right? Times this factor. And this one is spherical harmonic theta phi for gamma equals 0, which when gamma equals 0 means that theta equals theta prime, phi equals to phi prime. So that's the term that we were looking for in the first place. ALM is nothing less than the spherical harmonic calculated at theta prime and phi prime. So that's what the coefficient is. That's the coefficient we're looking for. That's the only thing missing to conclude the additional theorem, right? Let's go back here. We had to find which one is this, because the rest is already there, right? There's a double sum, and you have this factor here. The only thing left is this function of theta prime and phi prime, we just discovered. Right here. And then we have the final result, right? This is the addition theorem in final form. Just recalling, right? This part here is PL of cosine gamma. I mean, before the expansion in terms of PL cosine gamma was this factor here times PL cosine gamma. Now we found a way to expand PL cosine gamma in terms of the angles subtended by x and x prime. So we have a final result. Okay. Well, one additional long lecture. I hope you guys. I hope my timeline index in the description of the video will help you guys to move through different points on the lecture. Okay. Well, that's all for today. I hope to see you next time. Bye-bye.